Section 2.4 is about the precise, or often I'll call it the formal, definition of a limit. I want to just address this section as a whole for a moment. This is in our curriculum here at Saddleback an optional topic. Okay, it's one that I always cover, whether I'm teaching the honors version or not. It's one I really need to cover when I'm teaching the honors version, because honors students, a lot of your worksheets for the rest of the semester are going to be using the precise or the formal definition of a limit. Okay, but I want to make sure that those of you who are not in the honors section realize that I would be covering this section whether I was teaching honors or not. So no blaming the honors students for having to do this section. It is, many students find, one of the harder sections of the semester. Not so much because the calculations that we're going to do are difficult, but just because it's fairly abstract. Okay, so I'm actually going to start with something that's concrete, an actual real-world application of the concepts that are involved in formally defining what a limit is. And that's the notion of tolerance. Tolerance has to deal with measured quantities that we have, and it's basically an acceptable amount of error. So if you think about medication, if you have to take some medication, you're generally prescribed a certain dosage. So maybe you're supposed to take 3 milligrams of this medication. Well, when they create the pill or the vial of liquid medication that you're going to take, they've got to measure that. And they may not measure it perfectly. So there's some tolerance. So if it's 3 milligrams within 0.02 milligrams, the tolerance would be 0.02. If you take less than that amount by 0.02 milligrams, you're still getting enough medication for it to do its job. If you're getting more than 3 milligrams by 0.02 milligrams, you're not taking so much medication that the side effects are going to be worse than not taking the medication in the first place. Okay, so it's sort of an acceptable amount of error. When you have a measuring tool, those of you taking science classes with labs, now I realize a lot of labs these days are being done actually online, but if you're able to actually go physically into a lab, a lot of measuring devices come with a tolerance. They say, we've tested this thing and we know that it's accurate within a certain amount. So the tolerance isn't so much the acceptable amount of error, but the maximum that you can expect if you use that tool. Okay, so let's just suppose that we are manufacturing, and we're going to manufacture coasters, those things that you put like a cup on to keep the table from getting wet, or if it's a cup of hot coffee or hot tea, you don't want the table to get too hot. So it's to protect the table. I never use these things because my furniture just isn't all that important to me. But my parents are pretty big on coasters. Okay, so we're going to be manufacturing coasters in the shape of squares. And let's just suppose that we want it to be 4 inches on each side. Okay, so I'm going to let X be the side length. And then A, which is a function of X, is going to be the area that I have here. So that would be X squared, and that's our area. Okay. Now, if I'm manufacturing these things, I know that if I'm trying to shoot for 4 inches, I'm going to call that X naught. That's my desired value for X. That would be my 4 inches, but I'm going to have to measure that. And I could be off by a little bit. I also know that A of X naught, this would be my desired area, and that would be 16. So the 4 would be inches, the 16 would be square inches. So I'm aiming to get these square coasters that have an area of 16 square inches. Okay. Now, I'm probably going to make some mistake in measuring the side length, and of course if I do that, that's going to affect the area. Okay. But the area is going to be relevant in terms of how much material I actually purchase in order to make these things. So let's suppose that we want the area to be within half of a square inch. Okay, so the tolerance for the area is, and I'm just going to write it as plus or minus 0.5 square inches, meaning that it's okay if we get too much area, so if we get an extra half of a square inch, and it's okay if we measure things too small, so we get a little bit less area. But that's essentially our goal. And then what I want to figure out is how precisely then do we need to measure the side lengths? Because I'm not actually going to measure the area. What I'm going to measure is the side lengths, and then I'm going to cut this out of whatever material I have. Okay. So here's sort of what's going on. If I put x on the horizontal axis and area, which is a function of x, on the vertical axis. Now here I'm just drawing things in quadrant 1 because x is a side length and a is an area. Neither of those things can be negative. But I know that area as a function of x is just x squared, and I know what that looks like. I also know that if I'm shooting to measure the side length to be 4, that would put the area at 16. Now obviously I'm using a different scale on the horizontal and the vertical axis here. Okay. But if we're saying that our tolerance for the area is plus or minus half of a square inch, we're saying, you know what, we're okay with it if we go a little too high or a little too low. Okay. So I'm okay if we go up to 16.5 or down to 15.5. If I'm anywhere within that range, that's good enough. Okay. Now, I am purposely not drawing this to scale here. If this distance was 16 square inches, this wouldn't be half of a square inch. It's almost like I sort of zoomed in on just this section because the tolerance is usually relatively small, and it would be hard to see that with the naked eye if I drew it to scale. So I just want to acknowledge I am purposely drawing this thing not to scale. Okay. But we're saying that we want the area to be within this range right here. So I'm going to just draw in as dotted lines here. Okay. This horizontal strip here that's in between these lines at a fixed area of 16.5 and a fixed area of 15.5, this is sort of the acceptable range. I want to make sure that I measure the side lengths in such a way that my area falls in between these two values. And I can sort of see where it will. It's going to be for this section of graph that I have right here. What I want to do is now translate this down to the x-axis to see how close to 4 do I need to measure things. So if I can control how accurately I measure the side lengths, that's going to determine how accurate the area is going to be. Okay, now I am sort of making an assumption here that I'm going to measure this side length with the same level of accuracy that I measure this side length. And I'm doing that because we're doing single variable calculus here. So x, side length, is my one variable. We'll be able to improve upon this if we go all the way to 3c, which is multivariable calculus. Then you can take into account that you might make one error measuring this side length and a different error measuring this side length. If you wanted to, you could even say, and I might not even get the angle to be perfect. I might not get a perfect right angle. How does that mess things up? But for our purposes right now, we really only know how to work with functions of just a single input variable. So we're going to make the simplifying assumption that any mistake I make with this side, I make the same mistake with this side. Okay, probably not completely realistic, but probably reasonable. If I'm measuring things, and I'm the person who's measuring things, and I'm using the same tool, maybe I or the tool am prone to over measuring things or under measuring things. But it's reasonable to think that I might make the same mistake on both sides. Now, if a different person used a different tool to measure this side than that side, then our simplifying assumption becomes a little bit less reasonable. Okay, so what I'm going to do is I can sort of see that this section of graph right here is the section that's within the region that I want to be in. So I'm going to just follow these endpoints down and see if I can figure out what those x values are. I can see there's one x value that's a little bit smaller than 4 that would take me to an area of 15.5. And there's one x value that's a little bit bigger than 4 that would take me to an area of 16.5. I should actually be able to figure out what those are. So I'm just going to call them x1 and x2. Okay, and let's see if we can't figure them out. I know that if I plug in x1 to this function, this area function, which has me square it, I'm going to get 15.5. Now, algebraically, that would mean x is one of two things, plus or minus the square root of 15.5. But I can see x is positive. It's a side length. Okay? So, my x1 is the positive square root of 15.5. Excellent. All right, let's take a look at x2. When I plug that into this area function, that's going to take me to this cap of 16.5. Again, algebraically, I would have two solutions. x2 could be plus or minus root 16.5. For this practical situation where x is a side length and I'm working with this graph, just the right side of my parabola, I know that x2 has to be the positive square root of 16.5. Excellent. Okay, so I can basically say now, if I measure x to be between these two values, then I'm going to be in pretty good shape. Then my area is going to be within the tolerance of the 16 square inches that I want. Okay. But what I'd like to do now is, rather than focus on what these x values are, is look at how close are they to 4. What is the distance? What's this horizontal distance right here? I'm just going to call it d1, for that's going to be the first distance that I calculate. And I can always calculate distance as just subtracting endpoints. Want to just make sure that to get a positive distance, I subtract the bigger from the minus the smaller. So I'm going to take right endpoint minus left endpoint. d1 would be 4 minus root 15.5. Okay. All right, d2, that's going to be this distance that I get here between 4 and x2. That's essentially the distance that I can go to the right of 4 and still have my area be in this acceptable range. Okay. So now my right endpoint becomes x2. So that's going to be root 16.5 minus 4. Okay. So here are two distances. Now I could certainly get a decimal approximation of them if I wanted to using a calculator. But if I could figure out which of these is the smaller distance, that's going to be my tolerance for x. I want to choose the smaller one because I'm going to say if I measure x within whatever that smaller distance is, within that distance of 4, then I know I'm going to be in this acceptable range for x values, which puts me in this acceptable range for area values. Okay. I need to choose the smaller one because let's just take a look at an example. Let's suppose I had a point here A and I had some point over here B, and I'm saying D1 is the distance between A and B. And then I had some point C and I said, okay, D2 is the distance between A and C. Okay. Now clearly as I've drawn this, D1 is bigger. I can see if this is my acceptable region to be in, I can go that distance to the left and I'm good. But if I tried to go that distance to the right, I've gone outside of this region between B and C. On the other hand, if I take my smaller distance, I can go that far to the left and I'm still in this acceptable region. So the smaller of the two distances is the distance that I can safely go on either side of 4. Okay. Now, to see which of these is smaller, I could certainly plug into a calculator and just look at the smaller of those two things. But let's suppose I'm doing this on a proctored exam or a quiz, and I want to know which distance is smaller, and I'm not allowed to use a calculator. I can figure out which distance is smaller. Now, I'm not doing it just by the fact that it looks like this one is smaller, because I said I wasn't drawing things perfectly to scale. Okay. But I do know that this squaring function gets steeper as we move further to the right. So I know that we're steeper here than we are here. But I know that the vertical distance from 16 to 16.5 is the same as the vertical distance from 15.5 to 16, because that was the tolerance that we had for our area. If the graph is steeper here, it's going to cover that same vertical distance over a shorter horizontal distance. So where the graph is steeper, if you've got the same vertical change, that's where you're going to have the smaller horizontal change. So this one is the smaller of the two, and the smaller of the two is the tolerance for x. So if I were in manufacturing, I probably would get a decimal approximation of this, and then I'd say, okay, I've got to be accurate within, see, do I have a calculator here? I don't have a calculator lying around. Okay, within this amount, which would be more easy to work with if I got a decimal approximation. And so quality control people would know to check that the measurers and the measuring tools were always accurate within this amount.